So the last thing we're going to look at, remember this unit deals with means. Okay? Confidence intervals involving means, hypothesis tests involving means, just to refresh your memory. Unit 7 was proportions. Okay? There is, sorry, I don't know what you would call this, kind of a special situation for a difference of means. And it involves something that we looked at, a way of collecting data way back in Unit 4, that many of you had a little trouble wrapping your head around. And that was a matched pairs design. Do you remember what a matched pairs design was?
Isn't it with the matched pairs, typically you versus yourself, but one of you has only one of them has the thing you're testing?
Yes.
Composed of blocks made of two similar experimental units, a matched pair. Often the matched pair is the same unit randomly receiving both treatments random, like random.
Can you give me an example?
An example would be like the placebo effect. Remember when we were talking about placebo effect? So like there was a group of people receiving like a placebo and a real pill. So like a matched pairs would be two groups receiving it at random times. Both pills at random times.
It doesn't involve two groups.
But not
It involves two people.
experimental units. Not groups, units.
Okay, so you're saying that you would say take one person against another person, randomly flip a coin. One person receives the treatment, whatever it is, the other person receives the placebo.
And then the other person also, they both receive both treatments. Just like randomly.
Yeah. I'm just trying to think of an example where that would actually be done.
In random order.
Yes, you're right. I mean, matched pairs, it involves, yeah, it has to be done in random order. Like whatever the treatment and non-treatment.
Yeah, I just don't know what the units are. Like, I don't know.
Well, the example that, one of the examples I gave was if you're comparing ability of something. You're comparing, no, how can I say this? Maybe you're comparing the effectiveness of something.
Yeah.
So what you do, and maybe it's something about, I don't know, something health related. A new type of serum or something like that. Some type of liquid that gets you in which you can your stamina increases or something like that. So let's say you would want to compare long distance runners because that's about stamina, right? So what you could do, I mean, is you could do it one of two ways. You could say take people from a group of long distance runners, take the two best ones and pair them off against each other. One gets the serum or one gets the special cocktail. The other one just gets a similar looking cocktail. Okay. And then it's randomly decided. Or you can do it just over an extended period of time against yourself. So, you know, you would say, okay, we want you to drink this, and you don't know if it's the real or what they're trying to test the effectiveness of, or whether it's the placebo, and then do it 2 days later or something like that with the other one, something like that. Okay, so yeah, we do have an idea of the matched pairs, okay? And matched pairs can actually apply to confidence intervals and hypothesis tests involving means. So what we're going to look at is climate change real? Or is it a hoax? Okay, I think I pretty much know what all of you would think. along what I would think, but let's consider this. Okay, there was a book written in the early 2000s, State of Fear, by an author who actually was has a background in medicine, Michael Crichton. And it was about, what was it about? It was about terrorists, eco-terrorists planning planning disastrous events to support their idea that we have to do something about global warming. Okay, so they were eco-terrorists, right? Does it say? Oh yeah, plotting mass murder for the sake of propping up their false theory of global warming. So it's framed as fiction, but it does contain a lot of graphs of real data, okay, and an extended bibliography. So a lot of people kind of read it and went, I wonder about climate change. I wonder about global warming, including government representatives. So what we want to look at, and sort of what was sort of pushed in the book that we want to examine, is it actually real? Well, what they did in the book, okay, and this is quote, they were just talking about one of the, a place on Earth and a weather station there. So it's the record from the weather station at Punta Arenas near here. It's the closest city to Antarctica in the world. He tapped the chart and laughed. There's your global warming. Well, from I think it was 50. I can't read that. No, it can't be 50 years. I can't. Anyway, from here to here, what's happening to the temperature, global temperature? It's kind of decreasing a little bit, right? That's what the graph seems to. This is where Punta Arenas is located, the tip of South America. Okay.
Is it cold there?
Yeah. Okay. So what's the general trend shown in the chart from the weather station, and how does it support the author Crichton's skepticism of global warming? Well, it seems to show. Can I read it there? Oh, 1988. That's right. So from 1988,
Yeah.
1888.
1888 to 2004.
Oh, because it's going up by 4 years. Sorry. 1888 to 2004. There was a slight decline in temperature, or average temperature. Okay. Casting doubt on global warming. So imagine, you know, how people, skeptics of it, or people who are basically against it for political, economic, whatever reasons, sort of grab onto this and say, well, look, this is a place close to Antarctica, right? And I mean, if we're that close to Antarctica and it's not getting colder, maybe the entire Earth is not getting colder. But so if we look at the temperature change here, and if we start in the 1900s or 1901, and we go 50 years, and then we go 50 years again, so the average temperature over those 50 years was this, the average temperature over the next 50 years was that. So the difference between them is a negative difference, again, suggesting that's again suggesting that there was a cooling down. Not very much, a slight, but it was still going down. Okay, but I'm sure you guys can see the potential problem with this, which would be what, before we even flip the page? What would you say to somebody who presented this to you as a critical thinker who has a background in statistics? What would you say?
I was gonna say some kind of climate change.
Okay, let's say global warming.
Well, I feel like it's supposed to be stats.
Sorry?
I feel like it's supposed to be stats. Because it's not like global warming, it's climate change. Warmer aspect. It should be more warming.
Okay, but what about somebody who does believe in that the climate is changing and the earth is warming? They would look at this and say, what? Somebody's trying to convince them otherwise, and they say, here, look at this stuff.
Well,
And you would say,
and
what's that?
one, right?
It's one place
Yeah, and also,
in the world. Maybe what we should do is look at a lot of places in the world, all over the place, whether they be south, near Antarctica, north, near the Arctic, or in the middle. Okay? One of the things you should probably say is, yeah, but it's only one place. I'll be more convinced if this happens at a whole bunch of places. So, that's exactly what happened. Okay? So instead of one location, what's the average trend across many stations? So out of over 7,500 stations across the world, we randomly sampled 32 of them. Okay? And then we basically took each one and paired up their average temperature from 1901 to 1950. And then from 1951 to 2000. Okay, and then found their difference. So it follows a matched pairs structure. And by a matched pairs structure, okay, each station has two measurements. Along with the difference. Okay, and why is a matched pair structure good? It's good for controlling variation. Between stations. You don't want to do it just for one. You don't want to do it just for two. Okay? Because there's a lot of potential variation there. You want to pick a significant number so that the variation is going to be down, and the matched pairs along with that helps you to do that. So that's what happened. So all of the differences were found, and you can even just look at the table here. Look how many are negative values. Like without even having to calculate the average of this first, there's Punta Arenas, the one we calculated. Okay. But if you look at the rest of the values, 1, 2, 3, looks like 3 more sorry, 4. 4 more are negatives, which means the rest would be positive. So 5 negative, 27 positive. That's starting to get us to think. Well, there's a lot more that had positive. Well, in order to quantify that a little bit more, okay, let's find the actual average of all those differences, of all those samples, or the sample mean. And if you calculate the sample mean, you're going to get 0.35 degrees Celsius, which is about there. And notice where the negatives like start, well, this is slightly negative, so the negatives start here. The positives are all that section. Okay.
Maybe it's life skill.
Good question. What would you say?
I would say this is life skill.
Really? Why?
Because 0's here, and then it's like,
But it doesn't have to, 0 doesn't have to be the mean.
but there's more positive.
Doesn't matter.
I don't know then. If you ask me why.
Well, you're the one that brought it up.
Well, I'm asking you.
Oh, I see. Okay.
Well, if you think it's-
Remember, this is the mean.
Yeah.
Okay. So something that is roughly symmetrical will look like this, or, I mean, it could look like this, or it could look like that.
Yeah.
All of those are roughly symmetrical. So what would you say about this one? Roughly symmetrical. Yeah, because it looks like, here's our mean around here, and we kind of go like that, and we kind of go like that. So it looks pretty symmetrical.
Okay.
Yeah. No, that's a good question. Did more stations see warming during the 1900s or cooling during the 1900s? Well, more saw warming. We just talked about this. And we're actually, we counted how many there were. There were 27 of them. Okay. And how do you know? We can know by the table that we were given, or the dot plot that it was converted to. And does Punta Arenas appear to be representative of the general trend? Obviously not. Okay. Which suggests evidence is lacking. Or basically what he did is he selected data that worked for what he wanted to argue. Okay? Which was not good statistics. In other words, he was cherry picking data. Okay? And an example we already found. That. And would that be more representative? Yes, obviously. Okay. Yes. Because the average change of many locations is more representative than the change in just one location. This is kind of one thing that, I sort of hope you got out of this course is to kind of be prepared to look at things a little skeptically. And some things aren't just, well, that's got to be true because the internet said so. Don't, you guys are well beyond that. Here's where we can actually do some statistics with it. We can do what's called a matched pair T interval. Remember T interval because we're dealing with mean, right? Z interval was proportions. Or we can do a matched pair T test, either one, and it'll give us this, it'll give us different information, but the same conclusion. Okay. So let's say that in addition, like here's the data, the average difference across the 32 stations was 0.35, and also the standard deviation, something we need to know, was 0.296. Okay. And we want to find, construct a 95% confidence interval for the true global average difference in temperature. In other words, the first half of 1900 minus the second half of 1900s. And we want to use that 4-step process. So here's how we would do it with a matched pairs. So state we are constructing a 95% confidence interval for the, what we'll call, for what we'll call mu d, or you could call it mu diff, which represents the true difference in temperatures. The true average difference in temperatures. The plan, well, it would actually be, like, I know when you see difference between two things, okay, but we're treating the difference as what we're looking at, right? Whereas when we did a difference between two means, we did like mu1 minus mu2. We've already calculated the difference. So it's not going to be a 2-sample T interval. It's going to be a 1-sample T interval. For the difference. And then we go to the conditions. Okay? So remember the conditions, and we're dealing with means again. So it's random, which is the same for both means and proportions. It's 10%, which is the same as the mean, or which is the same for means and proportions. But for means, we don't use large counts, we use large sample. We use large counts for proportions. So for random stations, and let's put STN apostrophe, were randomly selected. %, 32 stations is definitely less than 10%
of all the stations, of which there were, we were told, 7,520 stations. Large sample? What would I say? 32 greater than or equal to 30. Good. And therefore, when we jump to our graphing calculator, we're going to do a t-interval. So when you do a t-interval, you are going to be asked the sample mean. Then you will be asked the sample standard deviation, sample size, and sea level. And remember, confidence level is always entered as a decimal. And when you do that, you get 0.24328, which would be degrees Celsius, 0.45672. Oh, I made a mistake in my notes. I said we are 99%. I should say we are 95%. So we conclude we are 95% confident the interval 0.24328 degrees to 0.545672 degrees captures the true average difference in temperatures.
Now, I didn't ask this question, but I could ask it. Is this proof that global warming exists? Do we have convincing evidence that global warming exists?
Yeah.
Sorry, I should have said it that way. Why?
Because it doesn't contain.
Zero.
Right. There's no negatives. Right. They're all positive differences. Right. So yes.
So that's how we would use a t-interval.
If we wanted to do a t-test, okay, and I'll try not to repeat myself here.
So remember, this is a one sample t-test. So state, well, this is where we do our null hypothesis and our alternative hypothesis. And remember, we're not doing two separate measurements. We're doing the difference, one measurement. So the null hypothesis, the difference would be 0. That's the assumption. We want to test that the difference is actually going to be greater than 0. And then again, remember, you have to true average difference in temperatures. For the plan, well, we're doing a test, so and it's one sample t-test. If, and then remember, I'm just going to say conditions already met. I'm not going to go through all those again.
We did that on the last page.
So the do we're going to do t-test. And we have to enter the null mean, which is 0. Sample mean. Which is 0.35. Sample standard deviation, which is 0.296. Sample size 32. And we are trying to test if the true average is greater than the null. So this is the null. It doesn't say D in here, calculator. It's 0. And remember, this is where we're looking for the p-value, because it's telling us the probability of getting a result that we got. Okay. And if it's really low, that means it's unusual, which means we accept the alternate. If it's not, if it's higher than the p-value, that means same as usual. Well, you should get a really low one. I think it works out to 7 zeros. And then 1. Which is extremely low. So, very unusual. And then again, we should know how to answer when we're doing the test, because p-value is greater than alpha.
Less than alpha.
Sorry. .75. We reject HO. We have convincing evidence. Convincing evidence. Global warming is set.
And what we did on the previous page is consistent, right? It is consistent because all the differences were positive in the confidence interval. The p-value was extremely low in the hypothesis test, which essentially mean the same thing. Okay, so I'll just leave it at that. Okay,